Okay, so this is the review session for March 28th. And Sadie's got some questions for us.
Yeah. So this is actually just an example I saw, and I thought it
Oh,
was,
here, I may have to do something to, let's see. So you can share. Okay, you should be able to share your screen if you'd like now.
um, I have it on my iPad, so I don't know if I can do that, but
Oh, okay.
yeah, you're good. Um,
Well, we might be able to share that too. I share my iPad, but maybe that's more of a hassle than it's worth.
yeah, no, it's okay. Well, I'll just start with the test question. That's probably the easiest. So it's the one with which of the compounds shown below are meso?
Right?
I don't know
Okay.
what number that is. I just have the screenshot of it,
Should
but
I could probably open that up and find it.
yeah, I probably should have come more prepared, but I did just come from that thing. And I didn't want you to think that I was bailing.
All right. Well, that's good. Okay, so we'll just go to the preview then. Okay, and I'm gonna share this screen. Let's see, where's my
It might have been the last few
huh?
questions. See, no, maybe it's
I haven't shared it yet. Okay, so can you see that now?
hmm.
Okay, so let's just scroll down here, which is chiral rankings, stereogenic centers, relationships. This one here, 8.
Yeah. Um, so I just wanted to double check basically my reasoning with it.
Okay.
I figured it out unfortunately after I submitted the second quiz, but
Okay. Yep.
so the first one on there would be miso because they're like the different chirality, and then so if you like in theory rotated it, it would be
Right. So
this.
yeah, if you rotate it around the center bond with both of those benzene rings pointing down to the same direction, then the bromine also rotates around so it's up. And so each of those groups, the benzene rings, the bromines, and the hydrogens are all reflecting each other right down a plane of symmetry in the middle.
Okay. So if there are groups that are kind of diagonal like that, is that pretty the standard is to move it?
Well, I think what it does need to have is that if you're looking at some diagonal thing like that, the groups on one end have to be identical to the groups on the other, right? Because when we rotate it around, it has to create an actual mirror image.
Yeah.
So everything on one side has to reflect everything on the other side.
Okay. And then so that would make the second one not because when you flipped it, the it chirality would be opposite.
Correct.
Um, and then the third one is miso, just
Right.
because they're they can be split down the middle.
Right. And
And
well, yeah, so there's the two things. One is being this plane of symmetry. The other one is if you drew a mirror image compound of it, right? Just drew the mirror image off to the side, then it would be able to, the mirror image would superimpose with your starting structure, right? Because meso structures are achiral. So it means that they are the same as their mirror image.
so and just to be clear, because this is something I struggle with. The
Okay, yeah.
flipping and the rotating and the enantiomers and
Yeah, I
diastereomers.
know it's hard.
It doesn't, I think the 3D-ness of it doesn't translate in my head very well.
Right.
So when you do the mirror image of it, it still has two away bonds, but then you could just rotate it to be
Yeah, it would just rotate and just lay right down on top.
okay. And then the fourth one isn't miso because there's only one chiral center. Or I guess yeah.
Which one is the chiral center?
Oh, it's not even chiral at
Yeah,
all.
so there's not even a chiral center
Got it.
because both of those, right? We really have just two isopropyl groups on there. And so those two groups are the same,
Yeah.
right? And so that center carbon with the alcohol, it doesn't have four different groups on it.
Right. But I mean, so even if I guess if the center, that's not a good question. So never mind. But
Yeah,
and
so
then
this one is the case where you have to be careful that even though there's a wedge like this, it doesn't mean that that's necessarily a chiral center, right? Because the wedge, this is a methyl, this is a methyl, right? These are both the same, so that's not chiral. And because this group is the same as the group on the other side, right? So it means that this carbon doesn't have four different groups on it.
right. Yeah. Okay. And actually the next question too, there was lots of debate on that one. Obviously it's not the fourth one because the bonds have been moved.
Right. So what is the relationship between that fourth one and the starting one?
Diastereomer, or I guess it would be just constitutional isomer because they have
Constitutional
bonds.
isomers. That's right. Yep.
I said it. I'm gonna say it wrong and then immediately change my mind like a lot.
That's okay.
But
Hi, Camilla. Okay.
Hi.
so I think the issue that I have with this one, so like if you did the mirror image, it's the same.
Mm-hmm.
So it's a meso compound, which I don't think I realized. Um, so meso compounds they don't have enantiomers, right?
Right. Because
So
their mirror image will be the same as they are.
okay. So then the first one isn't an enantiomer, it's just a completely different thing. Like it's not,
No, in fact, it's completely the same.
well, or sorry, that's what I meant, but like it's not a stereoisomer. That's what I'm trying to say.
Right. It's not even an isomer, right? It's identical because if you take that one and you just flip it over, and those dashed bonds will be wedges, and you just set it right on top, and they're just identical.
Okay. Okay. And then the other two they're diastereomers, they're isomers.
Right. These are diastereomers of the starting material. What's the relationship between those two, the second and the third one?
Yeah. Um, well, it doesn't really matter because they have the same, so probably this is so silly of me. Um, they're either the same or enantiomers, and I don't know from just looking at it.
Mm-hmm. What do you think, Camilla? These two, the second.
Oh, I'm gonna go. I think they're the same because if you like flip it, it's the same, right?
Well, if you take it like this and flip it over, then, for example, if we start with this bottom one, this bromine that's pointing up, when you flip it over, it's on the bottom. When you flip it over, it's going to be on the top, but then it's going to be going down. It's going to switch from a wedge to a dashed line, right?
Mhm.
The dashed line is going to switch from a dash to a wedge.
So
And
those
so
are enantiomers.
so they're enantiomers, right?
Okay.
So in fact, if you take this bottom one, it's hard for me to show it, but if you take it like this and you just rotate it in the same plane, but you rotate it around and line it up so the two bromines on each molecule are facing each other, you'll see they're drawn as they're just as mirror images,
Yeah,
right?
that I
If
like the
this
concept
bromine
of
rotated up and was just facing this one, they'd both be wedges, and these two would both be dashed lines, right? So they would just have a mirror plane right between them. Can you see that? Do you know what I mean?
so hmm,
I could switch over to my iPad and draw those. Okay, here, let me open up a new one. Okay, I'm gonna stop sharing this and I am gonna go over to my iPad. Stop screen. Oops. Come on. All right, try it again. It made me download something and then it won't. Share. Oh. No, it doesn't want to do it. That's not good. Um, okay, so if we end up wanting to go to that, I may have to restart that or something. So let me try something else. This is not very good, but if I have two that are here, I'll show you in a second, that are like this. I don't know if you'll be able to. Okay, so essentially we have something like, come on. That's not going to work at all. It doesn't want to focus on that at all.
I think it's because you have the background unfocused, but
Oh, there, right in front. Oh, it's because I have it. Yeah, you're right. Well, and then it's backward, isn't it? That's not what. Okay. So we can just keep talking while I restart my iPad and maybe it'll share then. Yeah, so essentially we have these two, they're like this, right? And I want to take one and just rotate it up like this. Right? And if we do that, then that other one should end up being just, with the two facing each other. Come on. Okay. Waiting. Okay, let's see if I can do this now. Oh, is it doing it? No. Gosh. Yeah, I don't know what the issue is here. Maybe. Sorry about this. It's like you do it one time and it doesn't work, or it does work, and then you do it the next time and it doesn't. Let me see if it'll work with it plugged in. There. Okay. Uh, okay, so if I have, oops, okay, this is gonna, now what is it doing? Pencil is 100%. Oh, there we go. It's writing. Okay, so if we have two molecules that are like this. Can you see this?
Mhm.
Okay. Like this. So what I was talking about is that if we take this molecule and we just turn it around so it's facing this direction over here. Okay, so I'm just going to essentially take that and just twist it. And so it should, if I rotate it like that, this bottom, let's see, which tools do I have here? The bottom bromine will just rotate around and it will be facing this way. The bottom bromine, this bottom one, will then come around. Now that's the bottom one comes around to the top. This one comes around to here. And so it would be like this. Okay, and if we could, if I can maybe do this, if I can lower this into here, then hopefully we can see that there's a plane of symmetry right between these two. You see that? So
I feel like I always get confused because I see how there's a plane of symmetry and I see how those like they're like mirroring each other, but I don't understand how they aren't just the same thing.
oh, okay. So let's do something different here then. Let's take this bottom molecule and we're going to take an axis right through here. And I'm going to rotate this molecule like this.
Mhm.
Okay. So when I do that, this bottom bromine is going to rotate up to the top. It's pointing up. So when I flip it over, it's going to be on the bottom.
I see. So
Right.
even when you, because in my mind, when you just flipped it up like that, it became the same thing as the top one. But when you flip it, you have to change it from like,
Right. I always think about it as like flipping a pancake or something. If there's something on the top, when you flip it over, it has to be, it goes down, the
yeah,
raw part when you're flipping it is on top and you flip it over and then it becomes on the bottom.
got it.
Right. So if this one's going to go that way, this other one's going to reverse as well. Right. So this is still different than that one.
Okay.
So if you do any sort of flipping, you switch the chirality. Like if you do like horizontal or vertical.
Right. If you're going to flip it over from, if you're going to have the opposite side, if you have this face on the top and you're going to flip it over so that face is now on the bottom, then all of those wedges and dashed lines have to switch. Right? If you rotate it like I did the first time and it's still within the same plane, then they stay the same. Right?
Right. But I mean, if you just rotated this one, it would be facing in a different direction, right? Then it's an enantiomer.
Right. Yeah, so those two ended up being, right, these are both stereoisomers of this one. Right? Because they're different only in the three-dimensional orientation of certain bonds. All the bonds are attached at the same places, so they're different only in their stereochemistry. So they're stereoisomers, but they're not mirror images, so they're diastereomers. Right? So what we end up with is a molecule like this. If we just draw it without wedges and dashed lines, and we want to predict how many stereoisomers there are, right? Then we can say that the maximum number is 2 to the n, where n is the number of stereogenic centers. right? And here there's 2. So we have a maximum of 4, but because 2 of them end up being the same because they're meso, right? If we had a molecule that had 2 different groups, if we had an OH and a bromine, then all those 4 combinations would be different because we could never have that meso sense because these 2 groups are different from one another, right? By making them the same, we eliminate one of the possibilities.
Okay.
Okay, that's probably more than you needed for that. So do you have more questions on that? Should I bring back up the exam?
I did have one question on the exam for sure. It was the one about chapter 5 or 6 for the energies, not the graph, but like just with the K value and the 15.
15.
Yeah, so with the rate of a reaction depends on the energy change between reactants and products. I don't think I fully that was wrong. I don't think I fully understand what that is
Right.
trying to say and what's wrong with it.
Okay. So one of the big points from this chapter for us to keep in mind is really just what's the difference between thermodynamics and kinetics, right? So thermodynamics has to do with equilibria, right? How much of a product or a reactant form during the reaction, whether the equilibrium lies to the reactants or products. And that is controlled over the relative energies of the reactants and products. So the reaction will proceed to whatever side of the reaction is lower in energy. Okay. So the other thing is the kinetics, and that's all about the rate of the reaction. And what controls the rate of the reaction is not the energy between the reactants and products, but between the reactant and the activation barrier, or the transition state. Right? So in that statement, where it says the reaction rate depends upon the energy change of reactants or products, this is mixing up kinetics and thermodynamics. So the first part is talking about the rate, but the energy difference between reactants and products has to do with thermodynamics.
Okay.
Okay, so those 2 don't really relate, don't, cause one or the other.
So then the correct statement would probably be like the rate of the reaction depends on the energy change of the rate determining step.
Or of the reactant and the transition state.
Yeah.
Yeah, or depends upon the activation energy or something like that.
Okay, cool. And if you have something you want, Camille, like don't feel speaking up. I have like 5 questions. So
I just more had questions on like the chapter 9 problems from the Alex. Well, I just had one. And like just kind of the basics of chapter 9.
Okay.
So we could keep doing this for however long.
Okay. I think I only have like 1 or 2 more left on the test, and then I also would love to see the chapter 9. So the only pretty much other one that I was like not sure about was the next question. So for the SN2, so 16.
16. Yep.
The 1 and 2 I was confused about at first. So why is the BR with just the methyl group is better than the primary bromine on the cyclohexane?
Why is the bottom one better than the top one? Right. Well, SN2 is largely, as far as the alkyl halide goes, is largely controlled by steric hindrance. right? And so a methyl group, and because the nucleophile comes in from the side opposite of the leaving group, if we only have H's around on this side, then it's not hindered at all, essentially, right? And a primary one, so this is a primary alkyl halide, plus it has this cyclohexane, right? It has two H's, but if that nucleophile tries to come in from the backside here, it's going to get partially hindered by the presence of this other R group.
Okay.
Okay, so
That's
methyl halides are usually faster than primary alkyl halides, right? Faster than secondary, faster than tertiary. Right, so in this one, you don't really have to look at what the other stuff on the molecule is. You just have to recognize that this is methyl bromide, this one's primary, this secondary, and tertiary.
yeah, I was just double checking that the logic was steric hindrance
Yeah,
between the
exactly
top
right.
and bottom one. So
Yep, exactly right.
that's I think that's all I have for now. So we can go to chapter 9.
Okay. So Camilla, do you have those, any of them up to share? Or can we go and should I try to find them or?
Whatever's easiest. I just have this one on here that I like cannot figure out why it's not right, or like why what I have is not right.
Okay,
So I
you
can
want to just share that one?
Yeah, let me, how do I share on here?
You know, sometimes these don't actually grade quite right too, I'm finding,
Well,
but
I definitely don't think I'm right, but I
okay,
don't know what the right answer would be, I guess.
okay.
Share. Can you see my screen?
Yep,
Okay. Wait, can you see that problem?
yep.
Okay. Because I'm looking at it and I was looking at a different question. It had like PBR3 and then HBR, and like it
Mhm.
was, those two are different and you use
Mhm.
those two for different things, but I don't know what the difference is, or like how to know what this like should be, if that makes sense. What the reaction conditions above or
Right,
below.
okay. So for these epoxides, you know, they open up pretty easily just because there's so much angle strain within the ring, okay? But we can usually do them under kind of two different types of conditions. We can either do it under acidic conditions. So in those conditions, what we're essentially going to do is protonate the oxygen and make it into a better leaving group.
Okay.
Okay, so that's what we can do if we have a weak nucleophile. If we have a much stronger nucleophile, then we can just open it up directly under basic conditions.
Okay.
Okay, so in this case, because we're using hydrochloric acid, we're under acidic conditions. And
So
so,
I added the hydrochloric acid. Like that
oh,
was what
okay.
I thought the answer was. I'll erase. Wait, did I don't
So
actually
go
know.
up and let me just see what exactly the problem is. What do they ask you?
Add the
Okay,
necessary
add the
reaction condition.
necessary reaction conditions above or below the arrow. Also, if the major product is missing from the right-hand derive. Okay. Oh, I see. Okay.
So like this is what it gives me, so I have to add the
Yeah.
reaction.
Okay. Um,
And I added the HCl because I just assumed with the Cl or with
right,
the chlorine, like that would be it, you know. But I'm
right,
not understanding if I need to like add
right. So
more
the
or
issue here, I think, is if we with HCl, it'll protonate on the oxygen, make it into a better leaving group, right?
Mhm.
Then the chloride will come in from one side or the other. And it will come in on the backside and open up the epoxide ring. So I think the issue here isn't that you have the alcohol and the chloride. It's perhaps a issue of stereochemistry. Okay,
Okay.
because the stereochemistry at the position that the reaction where the chloride comes in is going to become inverted.
Okay.
Right? So here, let me just do a little scratch papering of my own. Or I can switch over to, okay, so that's
So
good.
would I need to change that, or would I need to add a major product or change that major product that it gives me?
Maybe.
Okay.
So that's what I'm thinking. I don't think that there's necessarily a way in one step, if the stereochemistry is wrong, to just go, to do it with the opposite stereochemistry,
Mhm.
with a chloride. But what would happen is, let me just see here.
There's also on the side tab, I don't know if you know, there's like an example tab that doesn't make you miss the question. And that
Right.
lets you
Yeah.
override.
Oh, that is the example is what like saves me on these things. Cause I just like, I look at that and I understand how that works. So for each one, I like wrote out how it works for that one. And then I do it for the one that it gives me and just do that over and over.
Mm-hmm.
The example is
Well,
really nice.
I don't know. This looks actually right to me, because the chloride came in from the bottom here, and this is back, and so that just flipped up. So the chloride just comes down in here. This comes off the top. So it seems like HCl is a reasonable reagent for that. Here, let me see. I don't want you to miss this or something. If we just try something else. Let me just see if I can. Oh, that's closed. So that's problem number 14, I guess it looked like.
Yes.
Okay, so let me see if I can pull it up and I can use a cheat sheet on my end. Assignments. Oh, yeah. Assignments. On each of these, though, there's a whole bunch of different options. There's a whole bunch of versions.
Yeah. Yeah. And all the examples that it would give me, it was like asking for different stuff. So like I didn't really know where to even go with this one, you know?
Right. Okay, so here's a similar one. Okay. Oops, I didn't want to solve that. Try another. Well, this one. Okay, let me just try something here. Oh, that's. Interesting. Okay. So it's not a matter of um, your product being wrong. It's that the chloride can come in from from the left side
Mhm.
or from the right side, and that gives two different products.
So that one's right. There just needs to be another product.
Right.
So HCl was right as well. I just need to write in the second column
Yes.
if it
So
went on.
essentially, when we have this compound and the if the chloride comes in from the other side, it gives the enantiomer of that product. So you're getting a racemic mixture, um, and that's what they're asking for. So
Okay.
yeah, so everything up to that point was right. It's just
Okay. I just need to draw it. So for this different one, so the CL is right here right now.
mhm.
If it came in, because if we're looking at this originally, where would it be up here? Like where would that go on the second one?
No, I think what you should do is just draw the mirror image of that one. Okay,
Mhm.
so it's gonna come in from the right.
So it's going to be like down
Yeah,
here.
the chlorine is gonna be down there,
Okay. And then like the OH up here.
right?
And then, whoa. And then these two would still be like
Right.
that.
Yep.
Okay. So that's the second option. Or that's the
Yes.
second product that it's looking for.
It should be. I looked at another problem. It was the same, except it was bromines instead of
Okay.
chlorines.
Okay, let's see. Yay. Okay, perfect. That makes sense. Because I was wondering, I was like, what? It has to be HCl. I was like, I don't know what
Right.
else they're
Yeah,
looking
no,
for
so
now.
that was right.
Okay. Okay.
Yeah, it's just sometimes not clear what level of detail and stuff
Yeah.
they want.
Yep. I never know how many
And
products.
whether they, whether how much you're paying attention to the stereoisomers or whether there's enantiomers or,
Yeah.
that kind of thing.
Yeah. That makes sense. Thank you.
Mhm.
Okay, how do I stop sharing? Okay. And then I also just like for each of them, like I get the process of it, like I get the how to do it, but I
Mhm.
don't understand any of like the whys, if that makes
Oh,
sense. I
mhm.
can do it, but I don't really know like what I'm looking at. I don't know if that's that's a pretty vague question,
Right, right.
but I feel like a lot of it like because again, I just like look at the examples and I like memorize kind of like the where to put what and what, but I don't know why.
Hmm.
So
Well,
I
I
don't know.
think, this chapter is really supposed to be just building on the last two, right?
Mhm. Yeah.
So if we're doing reactions of alcohols, right, we can do either substitutions or we can do elimination reactions,
Yeah.
right? The challenge with alcohols is that, an OH minus hydroxide is a poor leaving group.
Hmm.
So in general, what we have to do either substitution or elimination reactions of alcohols is to make better leaving groups.
And is that when you start doing like the protonation or like the water, like you add in the water in there and then you like
Right.
go based off of
Yeah.
that and
So if we
stuff?
have an OH, OH minus is a bad leaving group, but if we protonate that water, then we have protonate the OH, then we have a water molecule that's the leaving group. And because that's not basic at all, that is a very good leaving group.
Okay. That makes sense.
Or you can use these phosphorus or sulfur reagents, phosphorus tribromide or trichloride or thionyl chloride. And they all react with the alcohol to make a better leaving group.
Okay. That makes sense.
Because if you use for alcohols, a lot of times the opposite or the other extreme that we can sometimes do, like I just mentioned with the epoxides, is that you either make a better leaving group or sometimes you can just use a stronger nucleophile.
Hmm.
But with alcohols, if you use a stronger nucleophile, it's usually more basic, then it just ends up deprotonating the alcohol. And then, the alkoxide that forms, O minus that forms is even worse of a leaving group, right? So you can't take that approach.
Okay. Okay. Makes sense. Right. I think that's the question that I had.
Okay. So I do have some slides that cover some of this material that we can go over too.
Okay.
Emma, do you have any questions too?
I just had a specific question about like the 1-2 shift with the hydrides and the alkyls, but I don't know if that would totally change where you guys are at. So if that's gonna
Well,
change the
I don't know. I think that's fine. Okay, let me switch over to the slides that I made up, because I have a slide that goes for that. Let me see here. Review session. Yeah, so that's a good thing to cover too. Let's see. To be honest, I don't really know why in this book they wait till we're talking about the reactions of alcohols to introduce this concept. Okay, because really, anytime we're forming a carbocation, this kind of alkyl or hydride shifts can take place. And really, so really the driving force for all of this, and I'm not sure if I have really necessarily examples that are much better than the one, that you've already looked at. Oh, shoot. But if we had something, say, like this, right? And if we protonate this, and I'll just use an H plus now, we could think about specific acids, but it would protonate here. And we generate this protonated alcohol, essentially a water molecule now that's a good leaving group, and so it can come off. And so that leads to the formation of a carbocation like this. Here, let me just even draw in the hydrogen here, just so we, like this. Okay, so we've generated this secondary carbocation, which is okay, but we notice that right next to that carbocation, right over here, we have a pretty highly substituted position. Okay, and so what can happen is that one of these groups over here, and let's say, well, we'll just use these methyl groups here, but one of these groups can just jump one carbon over. Okay, it's going to take its electrons with it. And when it does that, we now have an H and a CH3 over there. We still have one CH3 over here. And now our plus is left behind. Okay, because when this bond broke and this migrated over here, the two electrons that are in this bond are used to make this new bond. All right, and so now this carbon, which is this carbon, is now lacking electrons, and so it has a plus charge.
I have a question.
Yeah.
So for this might be a stupid question, but when that like plus is moving, why is it better for it to be up top if is it because there's a CH3 with it versus just a hydrogen?
It is, because remember, so what's the difference? This bottom structure I have, what would we categorize that carbocation as? If the top one is secondary, what's the bottom one?
Tertiary.
Is it
Tertiary, right? Oops.
Oh, and that's better.
Right. So this one, gosh, I can't put this down. This one is tertiary, and tertiary is more stable than secondary.
Right.
Okay, so it's essentially going downhill in energy. It's still a carbocation, so it's not super stable versus the reactant or the products.
Yeah.
But it's more stable than that secondary carbocation.
Okay.
Okay, and it's because the alkyl groups themselves are kind of weak electron donating groups. And so they're helping kind of spread that charge out a little bit. The alkyl groups, the the methyl group here and this CH2 and this CH here are able to donate some electron density to this carbocation to make it more stable. It's a process they usually call hyperconjugation. I don't know if did the book talk about that?
I've only read a few chapters of it. I
Okay.
haven't read all.
So essentially hyperconjugation is if we have, let's say I'll draw it like this with a wedge and a dashed line. So here's our carbocation. So this could be whatever, R and R. And if this has a group that has a bond like this that can be in the same plane as that p orbital, right? Because the carbocation is sp2 hybridized, so it's planar and it has an empty p orbital. And so this bond over here, this carbon-hydrogen bond, or maybe one of these other bonds, if it can line up in the same plane as this p orbital, it can donate a little bit of electron density to that carbocation. All right. And the alkyl groups can do this, but if we had, let's say, let me change one of these to just an H, if we have this H right here, it has no electrons over here that it can donate. Okay, so the more alkyl groups that we have, a methyl or an ethyl or this, side of the chain, those kind of groups can do this hyperconjugation and donate electron density to stabilize the carbocation. So that's why a methyl carbocation is the least stable, because the H's can't donate any electron density to it, and it just increases secondary, tertiary, up like that. So yeah, the tertiary one at the bottom down here is going to be more stable. And then from here, depending upon kind of what our acid was, if that was, let's say, if this was HCl, then this might react with chloride that was left over. And this could just react with the carbocation. And so that would give us a CH3, chlorine, and a CH3 over here. Okay, if it's going to do, if we have some other weaker acid that's not a good nucleophile, like if we used something like sulfuric acid or phosphoric acid or something like that, then we'd have like the conjugate base. Let's say we have the conjugate base of sulfuric acid, and it could just remove this proton, and it would end up causing a dehydration reaction. And so then we would get the double bond like this. Okay, so if we didn't know that this 1,2 alkyl or 1,2 methyl shift was going to take place, and we use sulfuric acid, we would think that it would have to just eliminate to here, right? Because, if it's going to dehydrate, we can't do it over here because there's no hydrogen at that point. So we would think it would dehydrate like this. But because it's a secondary, it would go by this kind of E1 mechanism, and it forms this carbocation. And because we have this highly substituted position adjacent to the carbocation, that's why we get the alkyl shift. Okay, if up here, if it was just a 1 methyl and a hydrogen, then we could still have a similar type of thing that would go on. Oops. So if we started from here, okay, so then we could form, I'll skip a step here. I'm going to form the protonated one, and then I'm going to just draw the carbocation. So here would be our carbocation, and in this case, what do you think would shift? So we have a choice now. We could have either a methyl group shift like we did before, or we could have a hydrogen or a hydride shift. So which one do you think would be more favored? Let's just try it. Okay, so let's say, just like before, I'm gonna move this methyl group over to there. So that's a 1,2 methyl shift. I guess I'll keep it in red. So I've moved my methyl down here. There's still a H here, and the plus ends up here. Right? If alternatively, I shift the hydride over, then we end up, there was already one hydrogen there. We get a second hydrogen there. We have a methyl group, and then we have a plus like this. So which of those two intermediates, the red carbocation or the green carbocation, which one would be more stable?
The green one?
The green one. Correct. Why?
Because it is tertiary. And in the
Right.
top one, it's only connected to the 2 carbon.
Yeah, it's only secondary. In fact, this one here is just identical to this one, right?
Right.
Because it's just a secondary carbocation next to this, you know, this tertiary center, right? So it would be the green one here, that this one would be better in that case, right? So I guess you know, the kind of the point is that these, can I add another one here? Let's see if I can figure this out. I should use this more. I used this program more before, and I haven't done it as much.
I think you click, so go back to the slides. And there's
Over
like
there.
the 3 dots in the bottom left corner. And it should
Bottom.
say add page.
In the upper,
The bot of the actual slide, like it says 7, and then there's like a circle and 3 dots.
oh, I don't even see it.
Like there's like the side page that has like every slide you have, but little.
Over
And
here?
then you see, yeah, and then go up and to the left a little bit. There's a circle with 3
Oh,
dots.
right there.
And that will add a
Oh,
page.
I see.
So
So
if you
right
do that-
after that.
Yeah.
There. Add a page. Thank you.
Yep.
Yeah, so any of these ones, so like if we had, I guess some of the classic ones they probably have in the book, or if we end up with like a methyl groups like this, you know, this would be a case as well that we have a very highly substituted position adjacent to the carbocation. So it, in my opinion, and I don't know why they wait till this end, you know, we can generate this same carbocation. You know, we've seen we can do it from the OH, right? We protonate it and can come off. But we could also do it from a halide, right? And so what we're doing is essentially an SN1 or an E1 mechanism. right? So this could come off and it would generate that carbocation. In this bottom one, what we would have to do is we'd have to start here with the OH, and we would protonate it to form this water molecule, and then this could come off. So it doesn't matter, once we get to this carbocation, whether it started out as an alcohol or it started out as an alkyl halide. Once it's formed, we have this carbocation with this highly substituted center next to it, and one of these methyl groups can do a 1,2 methyl shift. So we have this methyl over here now. So there was already an H, so that's here. This, let's just draw this in as a methyl too. Methyl, methyl, methyl. And where's the plus going to be?
It should be on the left between the, or yeah, just somewhere
Right
around there.
here. So remember, when this bond, when this group moves over, it's going to take this pair of electrons with it. So what we could do, is here, let me try this just a little different here. Oh, not like that. I'm just going to draw this methyl group down here. And we have our plus here. So what essentially happens is we're going to just break this bond. We're going to take its electrons and it's going to attach over here. And now the plus is going to end up over here because that position is now short of electrons because those electrons were taken away from it. Okay, so you have to make sure that you're not like drawing arrows showing where carbocations are moving to, right? We show the electrons show where the arrows show where the electrons are going, and then the position that ends up being short of electrons, that's where the plus is. Right? So this would be another example where we could have this, 1,2 methyl shift. And it doesn't only have to be, hydrides or methyls. We could have an ethyl shift or a propyl group. They're just different alkyl kinds of shifts. Does that help, Emma? Or do you have another example or one that you were looking at that was tricky?
Well, I've got one. Yeah, that's just on my homework. So I start out, and I don't know if it's like the fact that it's a cyclobutanol that like threw me off, but I was having a really hard time with it.
Okay, do you have it up there? Do you want to share it?
I do. I can't screen share because I'm on my phone. I don't know if I
Okay.
can describe it. I'm so sorry.
Okay, no, that's fine.
But basically, yeah, so it's like a cyclobutane, and you've got like a methyl coming off the bottom, and then the other side is like a isopropyl, but one corner is an alcohol. Let me see if I can show you on my camera. That's not a very good description.
Well, here, let me share again. I can oh, I see. Okay, let me just
Is that visible? Yeah.
Okay. Oh, yeah, that's an interesting one. Okay, here, let me share mine. I've drawn it on here.
Awesome.
Yeah, I should have thought of an example like that because those are cool ones, I think.
Yeah.
Oh, I shared the wrong thing. Oh. Oh, there, it was just too slow. Okay, so here we have it down on the bottom right. Okay, so in this case, same kind of thing's going to happen. it's going to get protonated. Here, let me just move this up a little. Right? If we use sulfuric acid, then the alcohol with its non-bonding electrons is the most basic position, right? So that's going to pick up this proton. And it's going to form this water molecule here. It has a plus on the oxygen. So that makes it into a really good leaving group. So it's going to come off and take its electrons with it. And this is going to generate the carbocation with the carbocation here. So this is very similar with a small twist, right? It's similar to this case up here. Really, all we would have to do to make this case the same, here, let me just make a small change here, is if I just make this into a cyclobutane ring, then it's exactly the same. Right? Except what's going to happen. So we have some choices here. We have a secondary with a highly substituted. So we could either move a methyl group over, right? That would make a tertiary. Let's say if we did that, okay. Okay, I'm going to try it with this. I'm going to move this methyl group over, and I'm going to draw that way up here. That would give us an isopropyl out here now with a plus at this position. Okay, another possibility, which you might not even think of if you hadn't seen these kind of problems before, is that one of the carbons of the ring can move as well. So I'm going to move this one here. It's going to move over this way. Okay, so what I'm going to do here is I'm just going to redraw the same thing. Like this. And what I'm going to do is I'm just going to erase, oops, I wanted to erase just one bond. I guess I got to draw it in 4. I have it like this. I'm going to erase this bond, and I'm going to reconnect it to the position adjacent to it, to right here.
Oh.
And when I do that, plus is going to end up at the position where the electrons came from, right? And so that's going to be at this position right here, right? Because I just took this bond and moved it over. And so this carbon right here is now lost the bond, and it's just going over that way.
And so would that kind of rearrange into a nice little cyclopentane, it looks like, with that
Right,
charge
exactly.
on the
So
corner?
yeah, so sometimes if I do it like this, if I just draw and I erase it and redraw the bond, sometimes it looks pretty weird, but then I would just usually go and then redraw it in a better form, right? So now we have 5, so this equals a cyclopentane. We have a methyl and a methyl with a plus like this.
Okay.
Right? And so then that can do, the dehydration reaction or something like that. Right? And so it would just lose the proton over here to form the most stable the most stable double bond, the more highly substituted double bond.
Okay. Okay. So, and that would be the major product.
Right.
Is that right?
Yeah. So these kind of reactions, one of the key things here is not only that we're going, in this case, we did go from a secondary carbocation. This one's secondary, and this one's tertiary, which is good. This one is tertiary as well, right? But the cyclopentane ring system is more stable than the cyclobutane. Right? So if
Okay,
we're going to
there's less strain.
expand rings like this, it's, you know, it'll go from like 4 cyclobutane to cyclopentane, or if you had a cyclopentane, you could expand it to a cyclohexane, right? Because a cyclohexane is more stable than cyclopentane, but you wouldn't
Okay,
likely be able to go from a cyclohexane up to a cycloheptane, because cycloheptane then becomes less stable.
okay. Okay, so basically your goal with the cycloalkanes is to get the most stable ring possible when you're doing this
Well, yeah,
little
it's just the same with
shift.
all of these, right? Any of these hydride or alkyl shifts, we're just trying to generate a more stable carbocation. And when we have
Okay,
these cyclo rings, part of the thing that influences the stability of that carbocation is the ring size. And
okay,
along with the substitution.
okay, perfect. Thank you. That helps a lot. I really
Okay, good.
appreciate it. That
Good.
makes sense.
All right.
Okay, I have to run now, so
Yeah,
thank you
I
so
think
much for
we're
your
out of
help. I
time
really
too.
appreciate it.
Okay.
Okay. All
Yep, thanks
right.
for coming.
Thank you. See you next time.
Okay. Thanks, Eddie. Well, it was fun to have
Yep.
some of you show up this time.
Yeah.
Yeah.
Yeah, maybe
Sure.
I'll see you next week.
Yeah. Okay.
Okay, bye.
Thanks. Bye.